Assalamualaikum warahmatullahi taala wabarakatuh dan selamat petang. Bismillahirrahmanirrahim. So we continue our class. Today we need to understand the kinematics and then the what is meant by the dynamics. So actually what is a kinematics? So kinematic actually is a definition of kinematic is study the motion. So without the forces. So in this case, when we study kinematics, all the forces that add to the object is negligible. So we don't care about the forces if we study kinematics. But when we study dynamics, so we need to understand the motion or study the motion, so we have to take care of the forces that add to the object. Okay, so that is a comparison between kinematics and dynamics. Okay, so if we focus on the diagram, so we have the object with M, the mass is M, and the object move from here to the here, so they make the displacement as x, and the time taken is t is from t0 to the t, and then the object start with the initial velocity ux, and then vx is the final velocity. So in this case, vx is equal to 0. That means the object stop here. Okay, so the object is moving with the acceleration ax. Okay, so before I continue, so we just to remind about the free body diagram. So free body diagram, here is the direction for the positive x, and here is the direction of the positive y. So because in the linear motion in the y-axis, that's why we have to write all the acceleration ax, that means is referred to the x-axis ux, initial velocity to the x-axis, vx is the final velocity to the x-axis, displacement sx is a displacement to the x-axis, because we refer to this free body diagram. Okay, so I just to recall the kinematic equation. Sx is equal to uxt plus half axt squared. So vx equals to ux plus axt, vx power of 2 equals to the ux power of 2 plus 2ax, then plus the time the sx. So uva, u is the initial velocity, v is the final velocity, a is the acceleration of the object, s is the displacement, then are the vector quantity. So when we talk about the quarter quantity, so we need to take care the magnitude and then the direction. That's why we have to use the free body diagram for the direction. Okay, so in the kinematics, so actually we don't know why the box stop. So the initial velocity ux, and then the vx is equal to 0. So we don't care about how the box stop. So just we calculate all the initial velocity, final velocity, acceleration and displacement, and then the time taken. Because in this kinematic, we don't care about the forces. Okay, so we go for the dynamic. So at dynamic, so we have to take care of to consider the forces, so acting to the block or to the object. Okay, so the object is started from the ux, the initial velocity ux, and then the final velocity. In this case, the object is stopped, so that's why the vx is equal to 0. The object is stopped here, and then so because we need to to consider the forces. So we have the kinetic energy here. So the kinetic energy, initial kinetic energy, half mu x power of 2. And then we have here is a final kinetic energy, half mv x power of 2. Okay, so and then we apply the work. Work is the resultant force. Work is equal to resultant force times the displacement. Sx, that means here in the component x. X is here. Okay, and then we have the kinetic energy, final kinetic energy. We have the initial kinetic energy. And then we apply the work and energy theorem. So in this case, work is relative to the change in the kinetic energy. Work change in the kinetic energy, that means the modulus here, kinetic energy final minus the kinetic energy initial. And then we have here work as a resultant force times the displacement Sx, and then equals to the half mv x power of 2 minus half mu x power of 2. And then Fp is a resultant force, and then they can be related to the Newton's second law. Fp is equal to the max. Then we have to understand the resultant force that acting to the object. So in this case, we have the F here. Here is the applied force. And then we have the frictional force. And then because the object is moving here with the acceleration a, so F in the same direction with the ax, so we take as a positive. Then the frictional force is again direction of the a acceleration, so we take as a negative. That's why we have the F minus the Fg equals to the max. Then we can solve the problem to find the ax. Okay, when we get the ax, so that means we can use the ax to find the anything to find the initial velocity, final velocity, displacement, the time taken based on this kinematic equation. Okay, so and then so that means in the dynamics, so we know why the box stop. So because we consider the forces. Okay, so we continue. So we continue. So we refer to the inclined plane. So and then so we refer to the inclined plane. So object is moving upwards. So they act by the applied force F. So the object from here, they are moving upwards to here. So with the acceleration A. So that means the object is moving outward. So with the acceleration A. So from here, and then they go to up here. So we have the initial velocity U, and then we have the final velocity V. We also have the height. One is your initial height, and then here is the HF is the final height. Okay, so before we continue, so I just to remind about the weight of the objects. Let's say the object is now is here, so we have the weight downwards, and then we can resolve to here is a mg cos theta, and then we are resolving here, so the mg sin theta. So mg cos theta is here, mg sin theta here. So we are resolving the weight of the object to this, to here. We got the mg cos theta, and then here we have the mg sin theta. Okay, first thing, and then we go for the second is the frictional force. So the frictional force is the Fg. Then we have Fg is equal to the mu r. Mu is the coefficient of friction. Then R is the normal force. Then normal force actually is R here is balanced by the mg cos here. So that's why your R is mg cos theta. The R balanced by the mg cos theta here. So that's why we have the frictional force we can write as a mu mg cos theta. And then take notes, as usual, force in the same direction of acceleration, that means same direction with the acceleration, we take as a positive. Okay, so we go for the work and energy theorem. So in this case, we have two cases here. So work and energy theorem refer to the change in the kinetic energy, and here is change in the gravitational potential energy. So work, so we write as the resultant force times the displacement. Change of kinetic energy final minus the kinetic energy initial. And then for the work and energy theorem refer to the gravitational potential energy, work as the resultant force times the displacement, and then change of the potential energy. So the mgh final minus mgh initial. So we can manipulate so we can get this equation. Okay, so we continue here. So we have the resultant force Fp is equal to the ma. That means is refer to the Newton's second law, and we need to understanding the friction the resultant force. So resultant force, then we refer to the diagram here. See, F is same direction with the A, so we take as a positive. And then mg sine theta is against direction of the A, so we take as a negative. And then the Fg also same against direction with the A, so we take as a negative. Then it equals to the ma. Therefore, we can manipulate this equation so we can find this value of the A. Okay, so and then we go for this work and energy refer to the gravitational potential energy. So we apply same Fp equals to the ma. Then we have the F minus mg sine theta minus Fg. So the same like here. Equals to A, then we can get the A. So after we got the A, the value of A, so from the A, then we can apply and use the kinematic equation to solve the problems. That means we can use all the kinematic equation, choose one, the best one, depends on the equation. So you can find either to find the S, or either to find the time taken, or either to find the final velocity or the initial velocity. So and then just to summarize here, so work and energy theorem actually is you can use the work and energy theorem to solve the problem that involve all the kinematic equation. For that is thank you.